Welcome once again to another lecture series on fluid mechanics. In the previous lecture, I have given an outline of the syllabus, started with the introductory part and some properties of fluids also. We have discussed like mass density, weight density, specific volume and specific gravity. If you haven't watched the first lecture, I provided the link below for reference for a quick revision. Now moving ahead, in this lecture, we will discuss very briefly about the topic called viscosity, whether it is dynamic viscosity, kinematic viscosity, effect of temperature on viscosity for both the liquid as well as gas we'll discuss, and also lastly but not the least, we'll also discuss the types of fluid. So let us now discuss viscosity, which is an important property of fluid. So how can we define viscosity? As you can see from the slide, so it is just resistance to flow of fluid, okay, one layer of fluid over another. Then viscosity is also called as fluid friction. And what is the reason behind this viscosity? What are the forces responsible for this viscosity? First one you can see the cohesive force, and the second one is intermolecular momentum transfer. Now what is cohesive force? It is the attraction between the same particle like water and water. Then intermolecular momentum transfer kya hai? This is the this occurs when the transfer of energy when the particles move from one place to another. Clear? Okay, let's get to know more about this viscosity with the help of this diagram. So below you can see a velocity profile diagram as I've given. Here you can see in the figure. So see, in the x-axis of this diagram we have the direction of flow of fluid, and in the y-axis, which is perpendicular to the x-axis, we have the your depth of flow. Okay, and let us also consider two fluid layers A and B, which is moving at a different velocity. Okay, now du is the difference in the velocity between these two layers A and B, and dy is the difference in distance between these two fluid layers A and B. Clear? Okay, now come to the bottom part of the diagram. See, the velocity at the bottom is 0 here, and it will increase as we move towards the y direction. Why this velocity is 0 here? It is because of the adhesion and van der Waals force, since it is maximum here. But as we move ahead away from the bottom part towards the depth towards the y direction, this will increase. Okay, that means your adhesion and van der Waals decreases as we move towards the y direction, so your velocity gets increased. Clear? Okay, since the two layers are moving at different velocity, like u plus du, A is having more velocity than u of the B layer, there is a relative motion between these two layers. Okay, there is a relative motion between these two layers A and B. Okay, since the upper layer is moving at a greater velocity than B, the upper layer will feel a resistance in its flow, and it is vice versa. Okay, that means the upper layer will exert, this upper layer A will exert a shear stress on the lower layer. Same way, the lower layer B will exert a shear stress on the upper layer during its movement of the fluid flow. Clear? And this shear stress, as denoted by tau, is proportional to the rate of change of velocity with respect to y. Okay, and mathematically we can represent this as tau is directly proportional to du by dy. This is change of velocity with respect to y, and we call it as velocity gradient. And if we remove this proportionality constant, tau is equal to mu into du by dy. So this particular equation we call it as the Newton's laws of viscosity. So let's learn now about Newton's laws of viscosity, which is given as shear stress is directly proportional to the rate of shear strength. Now let us find out this rate of shear strength. See here, I've drawn a simple diagram here. This is for a particular time interval. Okay, suppose let us consider a small you can say a small time interval dt, and also we have dy as a elemental height or elemental depth, and du, suppose let's say this is the velocity of the small element at a particular layer. Okay, and then let's say this line AB is the initial position of the particle. Okay, so what will be the velocity at this point A? It will be, velocity will be 0. Okay, UA will be 0. And what will be the velocity at this point B? It will be du, since we have considered du as the velocity of the small element. Okay, considering this as the fluid elemental layer. Okay, so now let's recall the your definition of fluid. What does it say? A fluid is a substance that deforms continuously under the action of a shear stress regardless of its magnitude. Okay, now suppose we have applied some small shear stress or shear stress of any magnitude, then at this particular time dt, that is a small time interval, how much distance it will cover. That means how much distance this your fluid element will cover, or it will get deformed. So distance covered will be du into dt, which is nothing but your velocity into time. Will get so at a particular time dt, it will cover a distance of du into dt. Okay, so let's represent this motion by a right angle triangle ABC. Okay, and dt is the angle of deformation. Okay, clear? So tan d theta is equal to, can be given as du into dt by dy. We can remove this tan since the theta is very small. So what remains? D theta is equal to du into dt by dy. If we do some rearrangement, you can have d theta by dt is equal to du by dy. So see here, du by dy, what is this? This is change of velocity with respect to depth. So what we call this one? We call it as velocity gradient. So this is equal to what? D theta is what? I have said that d theta is the shear strength. Okay, so this shear strength is with respect to some particular time dt, so we call it as rate of shear strength. Okay, so keep in mind that your rate of shear strength is equal to the velocity gradient here. Okay, so how we can write this? So tau is directly proportional to either d theta by dt, or tau is directly proportional to du by dy. And we have the Newton's laws of viscosity as tau is equal to mu into du by dy, or d theta by dt also, you can use. Okay, so normally we have tau is equal to mu into du by dy. We call this as Newton's laws of viscosity. And your mu, simply we call it as dynamic viscosity or viscosity. Okay, exam you can find such objective questions. What is Newton's laws of viscosity? You have to choose between different formula, and you can just tick this one. Okay, and one more thing you can keep in mind is that sometimes in exam, often we have seen that sometimes it is asked in case of your units or units also. Okay, so let's try to see the units also for this viscosity. Let's see first for the SI unit. Okay, so we have the equation for Newton's laws of viscosity as tau is equal to mu into du by dy. Tau is what? This is force per unit area. So force is Newton per meter square is equal to mu into du by dy. So velocity meter per second. This is for du, and dy we have as meter. We need to find out the unit for this mu. So mu is equal to, we will do some rearrangement here. Mu is equal to Newton, you bring this here, Newton per meter square into s is second into meter for distance by meter. So meter and meter cancels out. So what remains? Newton second per meter square. And this Newton per meter square, we call this collectively as Pascal. Keep in mind. Okay, Newton per meter square, we call this collectively as Pascal into second. So for in SI unit, we have the unit for velocity, viscosity as Pascal second. Okay, so we have done the units for viscosity in SI unit. Okay, now let us also see the units of viscosity for the CGS and MKS system also. So first let's see the units for viscosity in CGS. It will be given as 9 seconds per centimeter square. Okay, how is it coming? See, for SI unit we have found out that it was Newton second per meter square, isn't it? So the unit of force in SI was Newton, so, but here in CGS your force unit will be dyne, and the rest will be same. Dyne second, and meter square changes into centimeter square. So Dienst-second centimeter square it is coming for, or as a unit of viscosity for CGS system. And this whole Dienst-second per centimeter square, we call this collectively as your poise. Okay. And then for MKS also we have viscosity as unit of viscosity as is equal to kg force second per meter square. Okay, clear. Let's see also the conversions of this different unit system. Okay, SI, CGS and MKS. So we have here you can see we have 1 kg force second per meter square, as you can see, is equal to 9.81 Newton second per meter square, or is equal to 98.1 poise. Let's see the conversion now. So therefore let's take 1 Newton second per meter square here. Then what will come if I take 1 Newton second per meter square here, then it will be 98.1 divided by 9.81 poise. So ultimately what it will become, so 1 Newton second per meter square is equal to 10 poise. So this is the conversion. Okay, suppose in numericals or objective question, if you have the units in SI or vice versa, the units in CGS, you can convert it either to CGS or SI unit. It's very clear. Or from here you can see 1 poise is equal to 1 by 10 Newton second per meter square. So you need to keep this thing in your mind to solve simple numericals so that you don't have any confusion. Okay, clear about this. So let's continue with the next viscosity, which is called your kinematic viscosity. And we represent this kinematic viscosity by the Greek word called nu, as you can see from here. And how do we define this one? It is defined as the ratio of viscosity. This is dynamic viscosity upon your density. It is defined as the ratio of viscosity upon density, and by density we mean here the mass density. Okay, so it becomes mathematically mu by rho. Same way, let's see the units also. So nu is equal to we have the units of dynamic viscosity previously as force into time by L square. Okay, so this is Newton second per meter square, same. And we have the units of density as mass per unit mass. This is mass m by volume. Okay, m by L cube. Clear? If you simplify this, it will come L square by 2. This is the unit of kinematic viscosity. How it is coming? See here, we have we know that your force is equal to mass into acceleration. Then what is acceleration? We have acceleration as velocity upon time. Okay, and what is velocity? Distance or displacement upon time, and by this mass it will become L by t square. This is for acceleration. Okay, then let's put into this equation for this force. Okay, so for force we have see mass into acceleration. Now we take this mass here, then acceleration we have L by t square into this t here. Okay, then we have this L square here into this density m by L cube. If you simplify this, then finally we are going to get this L square by t, which is the unit of your kinematic viscosity. Then it's become easy now, so we can have the unit of kinematic viscosity. Unit you have, so it will be L means like length, this is meter square, time means second. In SI it will be meter square per second for kinematic viscosity, and for CGS it will be centimeter square per second, and this centimeter square per second we call it as stroke also. Okay, so then 1 stroke is equal to centimeter square per second, or is equal to 1 by 100 whole to the power square meter square per second, or simplifying more is equal to 10 to power minus 4 meter square per second. And if you want in centi-stroke, it will be 1 by 100 stroke. So such unit conversion also you have to keep in your mind from your short answer type question. Sometimes it is often asked in your exams, your competitive exams. Okay. Let us also see the effect of temperature on the viscosity of fluid, whether it will increase or decrease. For liquid, the viscosity decreases with increase in temperature. Why so? Why is it happening? What is the reason behind? See, we know that your cohesive force and molecular momentum transfer, this were the main reason behind your viscosity, isn't it? We know this from previous lecture. So here, in case of liquid, what happens in case of liquid? The cohesive force predominates the molecular momentum transfer. Your cohesive force predominates the molecular momentum transfer. See, I have given one figure on the right side for liquid showing molecules. So for a liquid we have a closely packed molecules, as we can see from the figure, means the cohesive force predominates than the molecular momentum transfer, or we can say that we have much restriction to the molecular momentum. So therefore, what happens when temperature is increased in case of liquid, the cohesive force reduces. Okay, the cohesive force reduces its strength. So if the cohesive force reduces its strength, means these molecules can move more freely. More freely means, or in other words, you can say the viscosity is reduced with the increase in temperature, and which will ultimately lead to the flow of the liquid. So this is the effect of temperature on the viscosity of liquid with increase in temperature. Clear? Okay, so let's see for gas also. But for gas, keep in mind that it is not so. Okay, the viscosity increases with increase in temperature. This is for gas. This is contrary to the liquid. You have to keep this in mind. How is it happening? Now see, for gas, the molecular momentum transfer predominates your cohesive forces in case of a gas. See, and for gas, you can see from the figure, we have less, or you can say loosely packed molecules as compared to your liquids. Okay, so when we supply energy, or by increasing the temperature, the molecules, this individual molecule which are loosely packed, becomes excited. Okay, they become excited with more energy gaining, so thereby increasing their momentum. So when they have more energy, they try to move fast. So what happens when they move fast? They collide with each other. There will be collision with each other since they are moving very fast. And what will happen with this collision? It will bring a resistance. Okay, what is this resistance then? This is resistance is nothing but your viscosity, which is being provided with the increase in temperature. So for gas, your viscosity increase with the increase in temperature. Here we have the relationship between viscosity and temperature. See, for liquids, you can see from this mathematical expression that with increase in temperature of liquid, your viscosity decreases. Okay, this is the mathematical expression from where we can see the relationship between viscosity and temperature for liquid. Similarly, for gas also we have this expression as mu is equal to mu naught plus alpha T minus beta T square. So here it clearly shows that, or we can see that with increasing temperature for a gas, your viscosity increases. Okay. The next topic which we will discuss is the types of fluid, or the rheological behavior of fluid. So what do you mean by rheological behavior? It is the study of behavior of matter such as fluid when subjected to a shear stress. That means here we are going to see a matter such as fluid or gas, when it is subjected to some shear force, how will they flow? Okay, so that such properties we'll see here in this topic. So first one we have is ideal fluid, or types of fluid. In that first one we'll discuss is ideal fluid. So in order to be an ideal fluid, it should have some properties, isn't it? So the first property it will possess is incompressible. It should be incompressible. Then inviscid. Inviscid means no viscosity at all and no shear stress. Okay, so a fluid which is incompressible and has no viscosity, we call it as ideal fluid. But remember that in practical way, every fluid has some viscosity, isn't it? So ideal fluid is an imaginary fluid. Now why did I say that it has no, it will also have no shear stress? Just see in this equation I have given, you know this equation already, it is the Newton's laws of viscosity. So no viscosity means that this mu will be 0. So definitely if it's 0, then this right side will become 0. So I said that ideal fluid also will have the property of no shear stress. That means this tau will be 0 here. Clear? Okay. Next fluid we will discuss is your Newtonian fluid. So what is Newtonian fluid? a fluid which obeys Newton's laws of viscosity. Okay, and we know that Newton's laws of viscosity is given as your shear stress is directly proportional to the rate of shear strength. We have this one, isn't it? Now we see, if you try to see the rheological behavior of this Newtonian fluid, you can have a look at the diagram here. We have a plot of, on the x-axis, your velocity gradient du by dy, or in other words you can say rate of shear strength d theta by dt, and in y-axis we have your shear stress as represented by tau. So when we plot for the Newtonian fluid, we will have a straight line like this, and such a fluid which exhibits such behavior we call it as Newtonian fluid. Let's see, this equation is like you can see that it is similar to your straight line equation. Y is equal to mx plus c. Here your y is the tau. You can see from here your x is the du by dy, that is the velocity gradient, and m or the gradient is the mu. Okay, so c is 0. So when we plot this, we will have a straight line like this for a Newtonian fluid, and if the gradient, that means the slope of this one, will give you the viscosity. Okay, clear. Then let's proceed to the non-Newtonian fluid. Simple, which does not those fluid which does not obey Newton's laws of viscosity. Okay, so here for non-Newtonian fluid, we have the equation as tau is equal to m into du by dy to the power n. Such equation are called as power slope. Okay, this equation are known as power slope, and we have like your m as the consistency index and your n as the flow index. Okay, then on the basis of this n, that is flow index, we can have two types of non-Newtonian fluid with us. Okay, on the basis of this n, we can classify your non-Newtonian fluid into two types. First one is dilatant, or we call it shear thickening, in which your n, that is the flow index, will be greater than 1. And another one is pseudoplastic, or we call as shear thinning, in which your n is greater than 1. So why is the naming so? Let's see. Dilatant or shear thickening. Why? Shear thickening means when we apply a shear force to the fluid, okay, then viscosity increases. That means in case of a dilatant or shear thickening, when we apply some shear force on the fluid, the viscosity increases. Example, you can take starch solution. Okay, when you give some force or shear force into it, when you rotate it, then your solution becomes thicker. And see, if we try to plot the rheological behavior of this dilatant fluid, how will we do? You can have a look at this figure here. See, when we give the shear stress, your viscosity increases. So if you try to see the slope of this one, you can say that with the application of shear stress, your viscosity increases. An example you can take for this dilatant as starch solution. Okay, let's see the next one. Pseudoplastic. Shear thinning means it will be the opposite. So when we apply some shear stress to the fluid, your viscosity will decrease. Example, your blood, human blood. Okay, see, and how do we plot the diagram? There is one. See here, it will be something like this curve. Okay, see, when you try to see the get the slope or the gradient of this one, your see, with the application of your shear force, the viscosity decreases, and that means your n is less than 1. Okay. Next type of fluid we have is Bingham plastic fluid. Bingham plastic fluid. Okay, this is a type of fluid which needs some initial shear stress to flow. Okay, that means it requires some initial force so that the flow of the fluid can be initiated. Or we call such fluid as like which is neither a fluid nor a solid. Why do we call so? Let's see. Suppose, let's start with the Bingham plastic fluid first. Okay, suppose you have a you can say you imagine that you're holding a toothpaste upside down. So if you open the cap, it does not come down by its own, isn't it? So that is where your solid behavior is reflecting. Now if you squeeze or put some force into it, then your toothpaste comes out. That means it is again behaving like a fluid flow. That means it requires some initial yield stress so that the flow of the fluid can take place. The equation of Bingham plastic fluid is given by this one: tau is equal to tau y plus m into du by dy to the power n. N and m remains the same, and this tau y is what I have just mentioned here, the initial yield stress. So if you look into the figure here, come to the figure here, this is the initial yield stress which is required by such type of fluid, and after it reaches this initial yield stress, it starts flowing. And if the fluid flow obeys Newton's laws of viscosity, we call that as ideal plastic fluid or Bingham plastic fluid. Okay, then what about the fourth one, the Herschel-Buckley fluid? Same way. One more thing I would like to mention here is when it starts to flow for a Bingham plastic fluid, this m will be equal to mu, okay, and this n will be 1. Okay, again come back to the Herschel-Buckley fluid. It will also require the same initial yield stress, but it is behaving opposite to your Bingham plastic. So initial yield stress is required, then once the flow is initiated, it will not obey the Newton's laws of viscosity. Rather, it will flow like a non-Newtonian fluid, as you can see from the diagram given there. Okay, see from here, you can see from the diagram here, after the initial yield stress, the flow starts to take place, but it does not flow in a obeying in Newton's laws of viscosity. Rather, it flows in such a way that this obeys the non-Newtonian fluid, like this. Okay, so these are the types of fluid or rheological behavior fluid which you can study. So that was all for the this particular lecture series. In the next video lecture series, we will cover, or we will discuss on the topic surface tension, compressibility, bulk modulus, and cavitation. Thank you all.